Dear guests, I have the pleasure to present you the results of the seismic assessment of existing Swiss highway bridges and share with you some interesting case studies of seismic isolation as an effective technique for seismic retrofit. At the beginning of my presentation, I will talk briefly about the earthquake hazard in Switzerland. Following that, I will present the main results of the seismic safety assessment of existing Swiss highway bridges that took place from 2005 up to 2020. Based on these results, we'll see why seismic isolation was applied quite often as a retrofitting strategy. Demonstration of such seismic isolation case studies will follow. I will end my presentation with the main conclusions. The earthquake hazard in Switzerland is classified as low to moderate compared to other countries. The magnitude maps show how often an earthquake of or above a certain size is expected to occur within a specific radius and period. The presented map shows the probability of an earthquake within a magnitude of 6 or higher within a radius of 50 km within 100 years, which represents the approximate life expectancy of a human being and the service life of a bridge. The canton of Wallis in the south of Switzerland remains the region with the highest risk, followed by the city of Basel in the north and followed by the canton of Grisons in the southeast. For the canton of Valais, the probability of an earthquake with a magnitude of 6 or greater within 100 years about 25%. The last earthquake of this magnitude occurred in the Upper Valais in 1946. Modern seismic standards were introduced in Switzerland only after 1989, when most of the bridges in the national road network were already built. Only about 19% of the bridges were built after 1989, according to what are now considered as modern earthquake standards, whereas the remaining 81% were built before such standards came into force. Those bridges were not designed to account for earthquakes or were designed insufficiently. A number of existing bridges may therefore be insufficiently safe against earthquakes according to the current seismic codes. In order to be able to identify these critical bridges with limited effort and prioritize therefore the interventions, a simple two-phases seismic assessment procedure has been developed. The Federal Roads Office began assessing the seismic safety of some 4,146 national road bridges using this simple procedure in 2005. In the first assessment phase, all bridges are roughly pre-assessed according to the specific criteria using a checklist in form of a flow chart as shown here. The choice of the criteria for the preliminary check was based upon experience of experts as well as on the feedback of the seismic performance of the different structural type road bridges according to their national experience. Firstly, the considered object is attributed to bridge class. If it belongs to a lifeline, it is detailed checked in a second phase. The same if its surface is more than 6,000 square meters. If the bridge is an integral frame bridge or delta leg bridge and the abutments are less than 7 meters high, it is considered safe and further investigation is not needed. If unseating provisions are not satisfied, it's again checked in detail. Finally, a detailed assessment is applied if the object presents some potential vulnerable points, such as Gerber joints, skewed geometry with an angle of more than 45 degrees, intermediate joints on piers, major differences in bedding stiffness between neighboring piers, and other particularities described in more detail in the related Congress article. From the total 4,146 national road bridges, 583 objects were classified as critical, the great majority of them being as expected bridges built before 1989, before modern seismic codes came into force. The detailed seismic verifications of 583 bridges have confirmed the necessity to proceed to seismic retrofitting measures for 242 of them, mainly bridges before 1989. From these, for 96 bridges, the retrofitting measures are already executed, and for the rest, for 146 bridges, the retrofitting measures must be executed until the end of 2035. As seen in the figure on the left, the expected damage to Swiss highway bridges after a seismic event, as defined in the current codes, concerns mainly the bearing of the piers for 48% of the cases, followed by the retrofitting needs for the piers themselves for 14% of cases, and damage to the abutments to 43% of cases. As necessary interventions to end an intermediate supports concerns 67% of the total retrofit cases, it may be convenient to think of seismic isolation as an appropriate retrofitting strategy. To evaluate the more appropriate earthquake retrofitting method, one should optimally consider the interaction of three structural properties: stiffness, load bearing resistance, deformation capacity. The conventional traditional solution of the increase of the load bearing resistance of piers, figure on the left, is often costly and not totally effective. Specifically, the increase of the moment bending resistance of the piers by means of steel or reinforced concrete jackets leads to an increase of the stiffness and thus to a reduction of the fundamental period. This leads to further higher needed resistance than the one targeted initially. A disproportional increase of the bearing resistance with regard to shear may decrease the ductility since failure mode passes from bending to shear. Furthermore, when it happens that the seismic action overpasses the design values, damage can be important in the piers and their foundation and can result to long-term interruption of the road network. Other solutions, as is shown in the figure on the right, such as the improvement of shear and bending resistance of piers, for instance, by means of carbon fiber reinforced wrapping, may be convenient for specific objects, but since it does not apply to all cases, it may not be considered as a general retrofitting strategy. Again, despite the enhanced seismic response and the increased ductility, the dissipation is obtained by damage of the structural element, which may be undesirable. Seismic isolation presents several advantages. It responds to the need to replace bearings, which was found to be the most current deficiency of the seismic assessment of Swiss bridges. Thanks to the combination of increasing period and increasing damping, seismic isolation results to significant reduction of seismic action and prevents unnecessary costly retrofitting of piers and abutments. With seismic isolation, we have dissipation on the devices than on the piers. Seismic isolation limits damage by events not covered by the codes. Finally, it allows the structure to remain elastic or quasi-elastic, maintaining the functionality after a seismic event, and thus providing redundancy to the designed lifelines of the road network. It presents, however, some disadvantages. It may also be costly in specific cases in short-term analysis, and large displacements may result in intervention in the expansion joint to assure the necessary deformation capacity. The following slide shows two examples of this retrofitting strategy from real cases in Switzerland. The Brunnen Bridge on the 9th Highway formerly consisted of a continuous 5-span deck and then a 9-span deck with an expansion joint on intermediate support here in the middle. The two bridge decks were fixed to the respective abutments in the longitudinal direction. In the transverse direction, the bridges are restrained on all supports. The total length of the two bridges is 270 meters. The spans are varying from 16 to 26 meters over the higher piers. The fixed longitudinal support of the two half decks on the abutments was in no way able to transfer the seismic forces. The very different heights of the piers and the abutments led to an uneven distribution of the stiffness, with the result that the very short supports were overloaded. In addition, there was a risk that the bridge girders would fall lengthwise at the expansion joint on the central support. By installing high damping rubber bearings on the critical short piers and in the abutments, the longitudinal bearing system was changed from a fixed system to a floating one. By clamping the two halves of the bridge together at the original expansion joint in the middle of the bridge, the risk of the unseating of the deck has been eliminated. The new bridge assembly, laying over a total of 16 rubber bearings, receives reduced seismic forces longitudinally transversally, thanks to the increased damping and thanks to the increase of the fundamental period to 2.5 seconds. Let's now a more complex case study. The twin bridges shown here are located in the municipality of Ridge and were built between 1985 and 1988. They allow the motorway to cross the Rhone River. Each bridge comprises 3 spans. The side spans are 55 meters long and the main span 143, presenting a joint in its middle. The superstructure of the bridge comprises a box girder, the webs of which are raised and form a variable height trough structure above the deck. The bridge is supported on short circular piers founded on drilled piles. The abutments are shallowly founded. As shown for the south bridge in the figure above, the bridge is held longitudinally by the fixed bearings of the two piers C1 and C2. Transversally, the bridge is held by the fixed bearings of piers C1 and C2, by the guided bearings in the abutments A2 and D2, and by the guided bearing in pier B2. The bridge was checked in 2014 according to the increased seismic standard requirements, resulting in a seismic deficiency of the guided bearings of the abutments, of the guided bearing of pier B2, of the fixed bearings of pier C1 and C2, as well as of the pier C1 and C2 themselves and their foundation. The seismic conformity coefficient, that is to say the ratio of the seismic resistance versus the seismic action of an element, was lowest for the piers C1 and C2, equal to 0.28, one as the safe case. This value is much lower than the threshold of 0.40, which according to the Swiss seismic standards for existing structures means that measures had to be carried out directly in first priority. In order to reduce the horizontal seismic forces and to avoid the extensive retrofitting measure, it was decided to seismically isolate the bridge. A new bearing concept was proposed to secure the structure and improve its performance in case of an earthquake. The proposed configuration contains a combination of fluid viscous dampers and pre-stressed damping springs. A fluid viscous damper does not prevent very slow displacements, such as those due to thermal variation. It reacts in the event of an earthquake and dissipates a lot of the introduced seismic energy. A pre-stressed damping spring combines the benefits of a fluid viscous damper and the pre-stressed hydraulic spring. In normal operation condition, it acts as a fixed point. The pre-stress force must be greater than the forces to be withstood while in service, such as thermal expansion, braking, and wind. During an earthquake, a pre-stressed damping spring dissipates energy and then returns the structure to its initial position. Indeed, in order to avoid the very costly retrofit of piers C1 and C2 and their foundation, the study concluded that the longitudinal earthquake force should be distributed over the piers, the bearings of the piers B1, B2, and C1 and C2, rather than concentrating everything on the bearings of the piers C1 and C2 alone. Pre-stressed damping springs have a relatively low damping capacity compared to fluid viscous dampers. It's therefore more efficient to have the fluid viscous dampers in parallel with the pre-stressed damping springs in order to reduce the seismic action by increasing the effective damping. The longitudinal pre-stressed damping springs are therefore positioned in the head of piers C1 and C2, which remain the fixed point of the structure in service that takes up the braking forces, while the fluid viscous dampers are positioned on bearings B1 and B2. This makes it possible to distribute the seismic load and relieves bearings C1 and C2 under seismic excitation in longitudinal direction. In transverse direction, the pre-stressed damping springs are doubled on the piers compared to the abutments. This is because the moving mass of the pier is much more greater than the moving mass of the abutments. The pre-stressed damping springs in the transverse direction can help to reduce the transverse deflection of the deck under transverse seismic excitation and avoid the shock that occurs at 50 mm of lateral displacement. It's worth mentioning that for the existing bridges, the position of all spatial seismic devices requires the conception of a steel structure. For new bridges, this can be optimized early in the design of the support system of the bridge. The diagram on this slide depicts the favorable effect of seismic isolation for the longitudinal direction. The effective damping prior to retrofit is only 5% related to damage in the concrete piers and their foundation. After the retrofitting measures with special seismic devices, a higher effective damping up to 29% is achieved. The fundamental period of the structure for the seismic excitation in the longitudinal direction increases from 1.16 seconds prior to retrofit to 2.09 seconds after retrofit. The combination of increase of effective damping and increase of the period results to a reduction of the seismic actions by a factor of 4. Consequently, a retrofit of the piers and their foundations is avoided. In the transverse direction, the dynamic analysis is more complex. The bending deformation of the deck slab reduces the effectiveness of the isolators, and the effective damping being limited to 7.1%. However, the increase of the fundamental period for the transverse excitation is getting larger from 1.12 prior to retrofit to 1.88 seconds, and thus we have a reduction of the seismic action. Here now we come to the main conclusions. The seismic verification of the national road bridges has shown the deficiencies. Deficiencies concern mainly the bearings of the piers and the abutments, and secondly, the piers themselves. This resulted in many cases to the choice of the seismic isolation as an effective retrofitting strategy. Seismic isolation can be applied in most cases without interruption of traffic and results to an important decrease of the seismic action due to increased damping and increase of the fundamental periods. When displacement is not a restraint, high damping rubber bearings or lead rubber bearings are often used devices. When it's needed to restrain displacements, other devices such as pre-stress damping springs and fluid viscous dampers can be the convenient solution. Thank you for your kind attention, and I will be glad to answer to your questions.